Okay, so welcome to the Jones seminar today. We have George Pharr, who is a professor of material science and engineering and the Eric Nye 59 chair at Texas A&M University. He received his bachelor's degree in mechanical engineering at Rice University and PhD in material science and engineering at Stanford. After which he was a postdoctoral fellow at the University of Cambridge, and then after that he's been a faculty member at Rice University, followed by being a faculty member at the University of Tennessee, where he was also department head and also employed by the Oak Ridge National Lab as well. And now he's back in Texas at Texas A&M University. George is actually a fellow of 3 professional societies, TMS, ASM, and MOS, and is a member of the National Academy of Engineering. And he's also been the editor of 2 different journals as well. So George is going to talk to us today about exploring the unusual world of small-scale mechanical behavior with nanoindentation. And we probably couldn't get anybody else in the world who's a greater expert on this topic to talk to us today. So thank you, George.
Well, thank you, Ian, for the opportunity to come up here. It is a very welcome opportunity because I flew in here from Texas yesterday, where for the last 2 months, we have had temperatures exceeding 100 degrees almost every day. And in many of those days, it was as high as 110. So it was really nice to step out into the Boston airport last night and have to put a jacket on. So thanks for giving us the weather. Also, this is my second time here, and I got kind of curious as to when I was here before, and I think I put it together today because I remember very distinctly that I went to a Gordon conference. I think it was at Colby Sawyer, which is kind of down the road, right? And I checked my CV, and I see that I gave a talk at Colby Sawyer in 1983. 1983. So that's exactly 40 years ago. Time flies when you're having fun, folks. I suspect most of you weren't even around 40 years ago. But at that time, the conference was also attended by Professor Harold Frost. I guess is still around a little bit. There's Harold. Harold was at the conference, and he drove me up here for the day to look around, and I got to meet some of the folks here. But that was probably about 40 years ago. So thank you, Harold. All right, what I'm going to do today is talk about what I've done for most of my professional life as a scientist, and that's developing this technique that's called nanoindentation. And for those of you who don't know, this is a technique that's used to measure mechanical properties at very small scales. We call it nanoindentation, so the word nano's in there. We rarely do things at the formal nanoscale. But we do things certainly at the submicron scale, 100 nanometers or so, and occasionally we get down to about 10 nanometers or so when we're making measurements. And what I'm going to do today, I was asked to give sort of a more general interest talk, and so what I did was to put together 2 different talks, pieces of 2 different talks. One of them is what I call Nanoindentation 101, which is, basic introductions to nanoindentation for folks that are scientists in nature but may not know anything about the technique. And then a couple of years ago, at the 30th anniversary of some of the work that we did that was sort of set the stage for this, there was a TMS symposium at a TMS meeting where I was asked to give a talk that was intended to be fun, and on nanoindentation. And so I put together a talk that was what I called the 10 most unusual things ever done with nanoindentation. And what I'm going to do today to sort of finish up a little bit is to go through some of those unusual things that nanoindentation has been used for. I call this exploring the unusual world of small-scale mechanical behavior with nanoindentation. It's unusual in two senses here today. One, we frequently see things at small scales that you wouldn't expect. And so I'm going to talk a little bit about those kinds of things. And then I'm also then going to talk about these crazy things that have been done with nanoindentation over the last 30 or 40 years. So first of all, what's the motivation for this? Well, we live in the nano generation, and there are lots of things that you may or may not be aware of that are nano in scale, and where the strength at that scale is really important. And I've got a few of those up here. Clearly, if you look at circuits and you look at semiconductor technology, you've got things that are clearly at the nanoscale. You might ask, why are the mechanical properties of those things important? Well, the answer to that is actually kind of interesting. It turns out that these things fail frequently because of mechanical problems. When you're heating up, when one of these things gets hot, substrate starts to expand faster than the wires on the surface do, or the interconnects on the surface do, then those interconnects can go into tension and they can actually fail. And so it's important to have a technique that can go in and probe those mechanical properties. Here's one that's very important to me these days because my wife just got one of these things last year. Artificial knees and hips, these things are becoming quite common. Nothing nano about that, right? Well, wrong. No, there are nano things there. Those the joints have parts that rub and potentially wear. And one of the things that you can do to improve the wear resistance of those things is to ion implant the surface. If you can take a piece of steel and you can implant the surface with ions of things like nitrogen and so on, they go into a depth of just a few microns. And in doing so, they dramatically improve the wear resistance of the material. And in fact, the original nano-indenter that was developed back in the 1980s, the purpose of it was to explore the mechanical behavior of those 1 or 2 micron regions in an ion-implanted steel part. And so there are nano things that are there. This is one that I've worked on quite a bit. This is a hard drive. These things are becoming antiquated. We're doing things with solid states these days. But that hard drive consists of a number of layers. The disk here has a number of layers on it that all have different purposes. The information is stored in this layer, which is a magnetic layer. It's basically, are we magnetized up or are we magnetized down? And that becomes the bit. But these things spin at about 3,600 RPM in a standard hard drive. And as they're spinning, you've got this read-write head that's sitting on top of the thing. And that read-write head is writing the information, making something magnetized, making a small region a bit magnetized, or it's reading it to determine whether or not it is in fact magnetized. So is it a 1 or is it a 0? And this head flies over the surface of this thing as it rotates. This head flies at a distance which is less than 5 nanometers. And so occasionally the head comes into contact with the magnetic layer, or with the disk. The magnetic layer is extremely soft. And if it weren't for a hard overcoat on the top of that, you would destroy all the information that's on the disk if you happened to land the head on top of the disk. So over the years, overcoats have been developed, extremely hard things. They're very much like diamond. They're called diamond-like coatings. These things are about 5 nanometers thick, and they protect they're extremely hard, and they very effectively protect the underlying layers, and for that reason are important in this technology. Now, how those things were developed involved probing their mechanical properties. I can come up with different ways to make these things, which way makes the best coating, which one makes the hardest coating, and we were very much involved with that. Lastly, there are lots of micro machines these days. This is a little bug, probably a mite or something. You can see there's a bunch of gears here. Here are some of those gears here. And there are lots of devices now that depend on these micro machines. And the micro machines themselves can be tested and calibrated by pushing on them with nano-indenters to determine exactly how stiff they are and how it is that they move around when you start pushing on them. Now, this one this crowd probably knows this, so I won't go into detail on this, but a lot of folks don't appreciate how big a nanometer is. And the way I like to start off on that is simply to say the smallest thing that we think of is our hair, right? Well, a hair is 50,000 nanometers, so it's not very small, actually. You go down a factor of 10, a spider silk is 5,000 nanometers, so we're still not really very small. We go down another factor of 10, and I'm going to show you today some of these things that we call nanopillars, which are something that we've tested with a nano-indenter, and I'll show you some unusual behavior that comes out when things get that small, and that thing right there is 1/100th of that, so you can see how small these things are in fact getting relative to a hair. And then if you continue on down, this was from about 10 years ago. That's a computer transistor. That computer transistor is about 50 nanometers across, and that's getting down to a scale that's certainly in the nanometer regime. Those things are down to about 20 nanometers now, if I understand the new technology. And we've used nanoindentation to go in and probe the mechanical properties of these things. So this is the instrument that we've developed, and there are several of these things now commercially available. They all work on basically the same principle. The idea is that we've got a diamond here, and the diamond normally takes on this triangular pyramidal shape. We like that one because we can make these things very sharp, and we can maintain this triangular pyramidal geometry down to very small depths by using these things. That diamond then is pushed into the specimen by this column, and the column itself is pushed by a coil and magnet assembly up here. So this is kind of like a loudspeaker. Loudspeaker is just a coil and magnet. And what you do is you simply apply current to the coil, and by applying current to the coil, there's a magnetic force that's produced here that pushes the indenter down into the specimen. We can do that with nanonewton precision. So we can apply very, very small forces, and we can control them simply by controlling the current to the coil. Now, as this thing goes down, then we know what the force is. It's whatever, it depends on what the current is. We then have a device in the system that allows us to measure how far this thing has moved. So we can measure the displacement of the indenter into the specimen. In our system, that is done with a 3-plate capacitor. The outer 2 plates are fixed. The inner plate moves with the column. And as the column then moves down, there's a change in the capacitance, which you can then measure. And if you design these things properly, you can then measure displacements as small as an angstrom. So we can measure angstrom displacements quite accurately by using this capacitance system. So what we then do with that thing is we do an experiment in which we are going to control the load and force the load up with time. And as we do that, we then also measure the displacement of the indenter. And then we then get a force displacement curve as we're pushing this indenter into the specimen. And during loading, that thing looks something like that. And when we unload, we get a different curve that comes down something like that. And the difference between the loading and the unloading has to do with the fact that during loading, we are both elastically and plastically deforming the material. Which plastically deform, we're making the hardness impression. But when we unload, the hardness impression is there for good, and most of the unloading is due to the elastic recovery rather than to plastic recovery. And the point is that we then have a force displacement record. Let's see, we don't want to do that. That's a meeting I'm supposed to be in this afternoon. We can measure these forces and displacements with very high precision and resolution, and we can make indentations that are a few tens of nanometers deep, things that you could never think about seeing with your naked eye. And we can get the force displacement data. And the issue then has been over time, how can you take that force displacement data and measure mechanical properties of materials? That data contains information that tells us things about the plasticity in the material and the elasticity in the material. And that's what we've worked on for the last 30 years or so. So that's what this is all about. So I'm not going to go into detail on how this is actually done, but suffice it to say that in 1992 we kind of put it all together, and this became probably the paper that started the nano-indentation. I don't want to call it a revolution, but certainly people using this technique in various fields. And the basic idea that we came up with was that we take this Berkovich indenter, we load it in, we unload it, we measure things that we can measure precisely as we're pushing this thing in and we're pulling it back. And the properties that, or the parameters that we measure are the maximum force, the maximum depth, and then this thing right here, which is the slope of the unloading curve up at the top, which we call the contact stiffness. It's basically how stiff is this contact as it unloads. It turns out then that from those three measured parameters, S, P, and H and the maxes, we can then determine something that we call the contact depth. The contact depth comes from those parameters there. The contact depth is the depth along the indenter along which the indenter makes contact with the specimen. If we then know precisely what the shape of the indenter is, and we know how far back it's making contact, we can figure out how big the hardness impression is, just from the geometry. And that comes from knowing something that we call the area function, that we have developed techniques for calibrating very precisely. Once we know the area of the contact, then we know the hardness, because the hardness is just whatever the load is, P max divided by whatever the contact area is. And then lastly, through this equation here, which I'm not going to go into detail on, but we published another paper in 1992 that explains where this comes from. But via this equation, we can determine something that we call the effective elastic modulus. The effective elastic modulus is just Young's modulus divided by 1 minus Poisson's ratio squared. And it's related to the slope, this unloading stiffness, and the square root of the contact area in the manner that's shown there. And so the idea is that from data like this, we can then determine both the hardness of the material, which is a basic measure of the resistance of the material to plastic deformation or permanent deformation, and we can measure the elastic modulus, or we can actually measure E over 1 minus nu squared, which is a measure of the resistance of the material to elastic deformation, or the elastic modulus. And it all comes out of that. And I'm not going to go into detail on that in this particular presentation. Now, another thing that happened with the nano-indenters happened in the 2000s. And that is that it was realized that this instrument is almost perfect for doing a different type of test. And that different type of test is what is now known commonly as pillar testing. I'm going to call it nano pushing or compression testing here. And the idea is that if we can make little pillars or columns, and I'll tell you how we do that here in a minute in materials, and these little pillars or columns are about 4 microns in diameter, it turns out that the forces that a nano-indenter can apply are almost perfect for doing compression tests in these things. So we can replace the indenter with a compression platen, and we can do a compression test on these things. And when you do that, you end up with compressive stress-strain data that looks like this. And this was a paper, not by us, but by Mike Uchik and a lot of other folks in 2004, which set the mechanical properties community on fire because people realized in this work that suddenly things that are measured at small scales are different than they are at large scales. And that shows in this plot of the stress-strain behavior. If you look carefully here, the red is a bulk stress, the stress-strain curve for a bulk material. And the colors then are progressively smaller and smaller diameter pillars. So 40 microns is the black, 20 microns is the blue, and we go all the way down to pillars that are only 5 microns in diameter, and those are the green ones that you see up here. And if you look at that data, you'll see quite, I think, convincingly that as you get smaller and smaller and smaller, the strength of the material is going up and up and up. And that gives rise to the expression that became popular at this time, which is smaller is stronger, right? I'm a tall guy, so I'm weak. But you small folks, there is an advantage to being short. You're going to be stronger. You also see there's a larger amount of scatter in that data, and that has also been the source of what in the world is going on here. And so a lot of work done with a nano-indenter because it's perfect in terms of its load application and its displacement measuring abilities for doing these kinds of experiments. Now, you can also pull on things. You can, in addition to, if you're clever and you've got ways to hold on to specimens, to grip them, you can do a tensile test as well. This is one that we did on a moly alloy fiber, which was 400 nanometers in diameter. These little things that are extracted from directionally solidified eutectic materials. If you can pick those things up and mount them and grip them, which we've done here inside of a focused ion beam scanning electron microscope, then you can actually pull as well. There's no reason. You just reverse the current to the coil and it pulls rather than pushes. And you can get force displacement curves in tension, which for these fibers look something like this. And you can't see it on this plot, but once again, smaller ends up being stronger. When you make these things really small, they end up getting stronger. Another tool that has been instrumental in this work is the focused ion beam, dual beam microscope. Have you got one here? Got a dual beam? Okay, and so you know about these things. Hopefully you know about these things. This is one that I had at University of Tennessee when I was there. Of course, the beauty of these things is that you can not only just do electron imaging to see what you're looking at, but you can use the focused ion beam as a sort of a nanoscale sandblasting tool. You can go down and you can use it to carve out shapes in materials. And then you can carve out a valley if you want to. In this case, we wrote something on the head of that pen, which then belongs to the chancellor at the University of Tennessee when we were trying to get some money out of him. And then from a more scientific standpoint, you can use these focused ion beams to carve out these little pillars that can be used to do these small scale tests. Or you can also carve out small cantilever beams like this one right here. This is a notched cantilever beam that you can then bring a nano-indenter in and push down on the end of that thing right there. And you can then measure forces and displacements and look for when that cantilever breaks and do fracture mechanics kinds of studies to study crack extension at small scales. Now, on this idea of smaller is stronger, I want to point out to you why that is, at least one reason that is. And that comes from some work that we did on these things that we call molybdenum alloy nanopillars. And these were done in conjunction with Iso George at Oak Ridge National Lab, who's a close collaborator with Dr. Baker. Iso is sort of a world expert in metallurgy and has really nice tools for growing, in this case, directionally solidified eutectic alloys. And so this is a directionally solidified eutectic of moly. These are nominally moly fibers that grow in a matrix of nickel aluminide. And so if you directionally solidify these things, the two phases then grow in that particular direction. And the moly grows as these fibers that are then embedded in a nickel aluminide matrix. And with preferential etching techniques, you can remove the matrix. And so you just go in and you chemically treat it, the matrix goes away, and you end up with an army of little pillars like that. And you can control the size of the pillar by controlling the directional solidification conditions. You can then go into these things with a flat punch like this and push on them. And when you push on them, you can get a load displacement curve like this. And when these things deform, they go bam. And when they go bam, they turn into pancakes. They turn from pillars into pancakes almost instantaneously. Well, what's most interesting about that is to take these loads and turn them into stresses, and take the displacements and turn them into strains. And when you do that, the loads, without showing you the curves, the strength of these things ends up being 10 gigapascals. Now, most of you probably don't have an appreciation for what 10 gigapascals is. But to put that in context, notice that a lot of high-strength steels, very high-strength steels, have a strength of about 1 gigapascal. So this stuff is 10 times stronger than high-strength steel. Okay? And it was that idea, or those kinds of observations, that we saw a lot of in the 2000 period. And it got people to wondering, why in the world is smaller stronger? Why in the world does that happen? As my old teacher, Oleg Sherby, would say, if you can really make a lot of that stuff, you need to get out of academia and go make buckets full of this stuff, because you'll be a very wealthy man. Okay? Unfortunately, it's not that easy. All right, why is smaller stronger? Well, for those of you who are in materials classes, you'll know that strength is related to the defects that are in the material. And the classic example of that is what happens in ceramics and glasses. This is some sort of ceramic material that's been glazed, and you can see that there are lots of cracks and things in there. And what limits the strength of this material is basically, as you start to stress it, one of those cracks is bigger than the rest, and that crack then propagates, and when it propagates, it just cuts through the material and busts it into two, and you end up with a mess, right? And so the point is, it's the defects in the material that are important. Now, in metals, the defects that are important, of course, are something different. And in metals, the defects that we know that control strength are the dislocations that are in the material. And presumably everybody in here kind of know what a dislocation is from some class. Don't need to talk about that too much. So it's got to do with the dislocations. The strength's got to do with the dislocations. Well, what's that got to do with the size of the material? Well, the way that I like to illustrate that is through this diagram, which with the basic idea being this, that these dislocations are controlling the strength in some sense, okay? But there's only so many dislocations in the material. And because of that, there is a natural spacing for the dislocations, which is somewhere usually between about 100 and 1,000 nanometers, so about 1/10 of a micron to about a micron for the natural spacing of those things. And let's now put that in perspective relative to the size of the specimen. So if the specimen is big relative to that spacing, then you've got lots of dislocations in there. And when you start to push on this pillar, what happens is you get to the point where the stress is big enough to move those dislocations. And when they start to move, the material plastically deforms, and that represents the yield strength of the material. Now, as you start to go down in size, however, you may actually get to the point that the specimen is smaller than the natural spacing of the dislocations. And under those circumstances, then there's a high probability that there will be no dislocations in that material. And if that's the case, then you have to stress it to the theoretical strength of the material in order to get it to deform. And the theoretical strength of the material is greater than the stress needed to cause a dislocation to move. And that is essentially what is going on in these things. When we get to these small specimens, we're getting fewer and fewer dislocations in there. And when you get no dislocations in there, they go to the theoretical strength of the material. So this becomes a very useful way to actually measure what the theoretical strength of the material is. Now, we know that's the case in this particular case because we've done, and I guess you can't see it, we've done TEM on as-grown pillars, and it's probably hard to tell there, but that thing is absolutely dislocation-free. There are no dislocations in these small pillars. On the other hand, if you take that thing and deform it a little bit, then you end up with dislocations all over the place. And so the strength goes down as you start to deform, as you start to plastically deform this thing, because you're actually putting dislocations into the material. You know, dislocations are good guys and bad guys. No dislocations, it's strong. Lots of dislocations, it's strong. But when you're in the middle, like Mama Bear, then you've got problems of strength. Okay? So that's one of the things that's come out of dislocations, or out of nanoindentation. Now, what were the original applications that we thought of for nanoindentation when we first started doing this? And there were several of them that we knew were going to come about. One was hip joints, surface-modified materials, where we ion implant or we treat the surface so that the surface properties are different from the bulk. Nanoindentation is one of the few techniques you can use to go in and probe that little region at the surface and find out what the properties are and how they may differ from the bulk properties of the materials. Thin films, particularly in the semiconductor industry. Turns out that the first, in the 1990s, semiconductors were developing at a very rapid pace, and the semiconductor companies wanted to know what the strength of those films were that they were depositing on those wafers. And that became extremely important to them. And this is where nanoindentation really starts to take off in a commercial sense, because at that point, semiconductor companies with deep pockets start buying nanoindenters or want nanoindenters, and they actually put them on semiconductor processing lines. You'll find these things if you go out to Intel and you look at their processing line, somewhere there's likely to be a nanoindenter in there checking on the quality of the thin films that they're putting down in the semiconductor devices. Frequently, there are materials with limited size. Just had one of those recently. Somebody came to me with a very small crystal, sort of about the size of a salt grain, of a special form of silicon nitride that cannot be grown in bulk form, and wanted to know what the properties of the stuff were, so that if they were special, then he might think about trying to make bigger pieces. And so when you've got limited size, that's another application for the technique. Composite materials. Here's a good one. This is a picture of a composite where you've clearly got two phases, lamellar eutectic. You've got two phases. You've got indentations all over that thing. Some of those indentations are big and some of them are small. And what's the same about all these indentations is the force that was applied to them. So the force was all the same. So what that means is that the small ones are in the harder phase and the big ones are in the softer phase. And in fact, if you look across here, that big one is in this. This is I think I don't have it on here. It's a chromium silicide eutectic. And the big ones are in the chromium phase and the small ones are in the chromium silicide phase. So you can use indentation to go in and probe the properties of the components of a composite material, even when they're down on sort of the micron scale. Hard coatings, we've got machine tool hard coatings like silicon nitride, thermal spray, so on, diamond-like carbon like we saw in the hard drive. And then lastly, weldments and joints. You know, the structure of a weld is very complex. And you can go use a nanoindentor to probe across and determine the properties of all the different layers that are in the weldment or a joint. And those were all things that we anticipated. But there were a lot of things have come about in the last 30 years that we did not anticipate. And so what I want to do now is to switch and talk about some of the unusual things that nanoindentation has been used for over the last 30 years or so. So this one's a serious one. Some of these things are serious and some of them are not so serious, okay? This is a serious one. This one came out very early. It was in 1991. One of the reasons for that is it comes out of Oak Ridge National Laboratory, and Warren Oliver was there at the time and we were developing the technique there. And these guys were geologists at the Oak Ridge National Laboratory. And they had this rock, this funny looking rock up here that's sort of really pretty when you look at it in color. This is a thin section that's viewed in polarized light. And you can see lots of different layers in here. So lots of striations and layers. And what the geologists know is that this rock is zircon, which is zirconium silicate, and it's got lots of impurities in it. And curiously, those impurities have radioactive elements in them. The radioactive elements being uranium and thorium. And the uranium and thorium contents in these layers is all different. And that's why they look like different layers. And so the question became, first of all, the first question that came up was, well, are the mechanical properties of these layers any different? Are they different? And so a nanoindenter was then, you can see the nanoindents in these things. They're here, and they're through the different layers. And from nanoindentation measurements, what was done was to measure what the hardness was as a function of position across this little box right here. And you can see that the hardness in some regions is really high, and the hardness in other regions is really low. Okay? And each one of those regions corresponds to one of those striations in that specimen. Well, you might ask, why in the world, if these are just impurities, why are the properties different? And the answer is that some of these layers have high impurity contents, and some of them have low impurity contents. And in the regions where the impurity contents are high, you have a lot of radioactive decay. And when you have a lot of radioactive decay, in this case by the emission of alpha particles, which are helium nuclei, then you can cause a crystalline material to become amorphous. And what has happened here is that over the eons that this rock has existed, some of these regions have become, that started off crystalline, have become amorphous due to the radioactive decay. And they can actually predict, there's a way to correlate how much radioactive decay there has been from the age of the rock and knowing the chemical composition of each of the layers, how much uranium and how much thorium there is in each of the layers. And from that, you can figure out what the dose is of alpha particles that have been emitted over the life of the rock. And the idea is the longer the dose, the higher the dose, the more probable it is it's going to be amorphous. It's going to go from crystalline to amorphous. And in fact, if you look at log dose and compare that, this is a backward scale. It goes from 3 down up to 10 here in a logarithmic scale. What you see is that where this stuff is hard, the dose is in fact small, and where this stuff, where it's hard, the dose is small. Whereas if where this stuff is soft, the dose is relatively high. And what's going on? They've since done a lot of TEM work on this thing, and they know that the soft layers are amorphous and the hard layers are crystalline. And this is all due to the radioactive decay and forcing this crystalline to amorphous phase transformation. So the geologists like to call this, then, the world's longest radiation damage experiment. Okay? 570 million years this rock has existed, and it's been decaying like this. Now, any grad students doing radiation damage in here? I don't see any hands. That's good, because one experiment takes 570 million years. Okay? Okay. All right. Here's another one that just blew my socks off when I first saw it. So this is in biology. This is wood. This is the cell from a tree. This is a section, a microtome section through a piece of wood. And you can see the cells here. Here's a wood cell, and here's a wood cell, so on and so forth. The middles of these things are hollow. And if you look here, you'll see that there are indentations running across here and across here and across here, in which they're measuring both the hardness and they're measuring the stiffness of the wood cells, of the walls. And here's a cartoon of what happens when you make the measurement. So here's this little row right here, that's that little road right there, and so on and so forth. And if you look at this thing, you see it's color-coded so that we're measuring the stiffness, which is like the elastic modulus. Just think of it as being the elastic modulus. And you'll see that over on this side of the cell, everything is pretty high, got a high stiffness. Whereas if you go on this side of the cell, everything's on the other end. It's on low stiffness. And that maybe by itself is not unusual. But when you look at a whole lot of cells in this thing, you realize they're all like that. That one side is stiff and the other side is spongy. And it's always the same size. Now, Mother Nature always does things with a purpose. What is the purpose of that? Why is one side stiff and the other side is not? I don't know the answer to that question either. Okay? And nobody has ever been able to tell me why it is that one side of the cell is stiff and the other side is not. So that would be a good one if you want to publish in a glossy journal, an important journal, these high impact things, figure that one out and you'll get a high impact publication out of it. All right, so here's one that then involves doing tensile tests. So this thing right here is a black widow spider. Everybody know what a black widow is? These things are nasty. You're not supposed to be bitten by a black widow. Okay? That's a black widow. By the way, it's the female black widow that's the nasty one. She eats the male after they mate, from what I understand. If you tape these things down and stick a pin into this thing called the spinneret, you can actually pull out a single fiber out of this thing. And you can do a test. You can do a tensile test on that single fiber. And these fibers have diameters that are, well, this one in particular, this one is about 500 nanometers. So you really couldn't see this thing with your naked eye. You can see it here because the light's reflecting off of it in sort of a funny way. So you do a tensile test on that, and there's the stress strain curve, and it's two of them, looks fairly reproducible. The yield stress is up here somewhere. It's about 70 megapascals. So I know a lot of pieces of aluminum that would yield at 70 megapascals. So stuff's pretty strong. And you can do lots of interesting tests on these things. And this group from UCLA does this kind of stuff all the time. And you may have seen a Nova show on making spider silks from goat milk. Anybody ever seen that one? Yeah, that's where the stuff is leading. How can we make synthetic spider silks that are super strong? And you can see this kind of thing is valuable to them because they can use this to actually test how strong these things are. Now, I found another interesting thing along those lines recently, and that is a spider that has the world record, the Guinness Book of World Records, for spider silk strength, and that's here. This is a spider, and you probably can't see it, but there's a web up around here. And that web has a strength of 1.5 gigapascals. Again, high-strength steel has a strength of 1.5 gigapascals. So this stuff is really, really strong. That spider catches birds to prey upon. And so it has a web that is in fact that strong, as strong as steel, to actually catch birds and prey upon them. That's a spider in Australia. Any Australians in here? And there's all kinds of nasty things in Australia. Australia's a wonderful place. I love it, but there's lots of nasty things down there, including these spiders. Okay, here's one that comes from the world of dental science, which is also kind of cool science in this particular case. This one has to do with the mechanical properties of the enamel in a tooth. And the enamel is this outer layer, that's the hard stuff on the outside of the tooth. And what was done in this case was to section through the tooth and then actually go in, and they made, I think it was 2,500 indents. This was in the old days when a graduate student had to do that one by one. So, 570 million years, you certainly don't want to do that. You probably don't want to do this either. But from that comes a map, and you can actually map the hardness and the modulus. And what's kind of interesting about this is that if you look at where this tooth is hard, it's hard right up in there. Why is it hard up there? Well, that's when you bite on a nut or you bite on a piece of ice and you want to crack it. You want whatever's biting to be hard, right? And so Mother Nature's done us a favor by making that stuff extremely hard right in there. On the other hand, if you look down here on the bottom, that stuff down there is not very hard. And in fact, that stuff down there has actually got a smaller modulus. And so it's stretchy, it's stretchier, it's spongier on the bottom. Now, why is that important? Well, that's important because when you bite down on that nut, you put this top surface into compression, but that whole tooth is bending like a beam. And the bottom surface is going into tension. And if it goes into tension, then you have the possibility that if there's a crack there, that a crack can extend. But if that material has a smaller modulus, then the driving force for that crack extension goes down. And so you've got a soft region on the bottom or a spongy region on the bottom that then helps to prevent the propagation of cracks down on the bottom of the enamel. So, as I said a minute ago, Mother Nature always does things intentionally. Now, that one's kind of obvious what's going on. Somebody's got to tell me what happens in the wood cell walls. Okay? Here's one that I'll do very briefly. Turns out that some people have decided that nanoindentation could be a good clinical diagnostic tool for determining the quality of bones. So, when you get older, your bones become more frail. You get osteoporosis and that kind of thing. And so the idea here was maybe we can test the quality of bone by doing indentation on the bone. Now, this isn't on dead people. This is on live people, okay? And so what they did was to develop this tool. It's called the osteoprobe. Came out in 2006. It has since been clinically approved. So if you've got problems with if you think you have problems with bone quality, they can use this thing to probe how strong your bone is. And the way that works is that there's this sharp thing right here that has an indenter tip on the inside of it. And the sharp thing right here goes through your skin. They do this mostly on your shin. It goes through your skin to the bone. Now, they anesthetize you before they do this. Local anesthesia takes care of this. You can't feel it. That thing goes through the skin to the bone, makes contact with the bone, and then they, via a mechanism that's in here, they push the indenter tip down into your bone and push it in and withdraw it and measure forces and displacements. And so they get the force displacement curves that occur as this thing goes into your bone. When they do that, then they've got force displacement curves. In the early days of this, when they didn't know what they were doing, they were interested in seeing if there was anything that they could tell whether one bone condition was different from another. And what they did was they went to the local meat store and bought a piece of steak that had a bone still in it. They cut the bone down the middle. They took one half of the bone and did some force displacement curves in the unbaked condition, and then took the other half, the mating side, and they cooked it for a while, just to give it this is thermal annealing, right? They thermally annealed this bone, and then did the same thing, and you can see that the behavior becomes very different. And they use that simply as a starting place for, can we actually see something in a force displacement curve that indicates that the bone quality has changed somehow. And since then, they figured it all out, and they've got it all worked out clinically, and they know what to look for in these curves to assess from these curves, assess what your bone quality is. So anybody ever has bone quality problems, ask for an osteoprobe nanoindentation test. One I'll just do very briefly. Another thing that happens is that cancer cells turn out to have different stiffnesses than regular cells. And so folks have used nanoindentation actually in an atomic force microscope. You can do this with AFMs as well, to go in and measure the stiffness of cells. And in this particular case, they knew exactly which cells were cancerous and which cells were not cancerous. And what they found in this study is that this was in human breast tissue, that in fact the cancerous stuff actually has a lower modulus on average than the stuff that's normal. And people in the field of cancer continue to use these things to try to understand exactly what's going on in cancer in cells. Here's one that's kind of fun. I won't go into the detail of it. Anybody know what RDX is? What's RDX? It's plastic explosive. So this is nanoindentation of a plastic explosive. And I will tell you, again, we got a lot of graduate students in here. This is something that if you're the faculty member, you get out of the building and you tell the graduate student, go in the lab and nanoindent the plastic explosive, right? So turns out, for reasons that I do not understand, that if the particles are small enough, they don't blow up. But yet there was a strong need to understand exactly how the stuff elastically and plastically deforms. And the reason for that is you want to make shape charges with this stuff. And the way that a shape charge performs depends on its plasticity and elasticity as it's actually blowing up. And so they used nanoindentation in this particular case to back out many of the fundamental mechanical properties of this RDX explosive. Here's a good one. This one I really like. Let's see, how much time we got? A couple of minutes? We'll quit. There has been nanoindentation of Van Gogh off oil paintings, and that has helped some of the conservators to better preserve some of these paintings. And don't ask me exactly how that all works, but they've done that. Here's one that comes out of a movie. So anybody recognize that? What is that from? Indiana Jones, right? That's Indiana Jones. That is this thing called Petra. There are copper artifacts that come from that thing, that they were very interested in understanding exactly how those things were made. And they did nanoindentation along these things to figure out whether these things were cast or whether they were forged. The hardness sort of tells the tale there. It turns out that these things were forged. They were beat with a hammer into these shapes. There's an interesting one. Nanoindentation of mummies. So if you've ever, on Nova, you may have seen a show about this dude right here, the Tyrolean Iceman, who came out of the bottom of a glacier in 1991. He appeared. They dated him, found out that he was 5,300 years old, that he fell into this glacier. They used nanoindentation to figure out what the Young's modulus of his skin was after 5,300 years of being in the glacier, and found out that Young's modulus had increased by about 33%, by about a third, and they somehow turn that into the fact that that's how he was able to be preserved, and I don't quite understand that one either. Another one from a movies. What's that? What movie? Jurassic Park, Velociraptor. This was interesting because this comes from a journal in paleontology. What they wanted to do was to try to determine whether the claws on Velociraptor were for disemboweling prey or for climbing trees. That's an important, great hypothesis, right? Yeah. Now, why climbing trees? Well, remember, there's this idea that dinosaurs turned into birds. And so the idea in this paper is that in order to become a bird, the first thing you have to do is get up high. And the only way you can get up high is to climb a tree. And so they wanted to know, I'm being serious, They wanted to know whether or not the claws on this thing were strong enough to actually climb a tree, or whether they would break off. Now, they've got claws, but they're all fossilized, and so they're not in a state that you really can measure the strength. But they found a living analog, and the living analog is this thing called the Eurasian eagle owl. And if you look at that claw, whoops, that thing looks amazingly like that claw. And so they went in, they did nanoindentation tests on this thing to determine how strong it was, and then did a bunch of finite element tests, simulations to determine whether the tip of that thing would break off as it was climbing a tree. And the answer is that he could climb the tree. So therefore, Velociraptor turned into a cardinal or a sparrow or something like that. And lastly, my favorite one of all times, and then we'll quit. And this comes from this young lady who was, at the time, she was in the 8th grade. She's the daughter of one of my postdoctoral students. So she had access to our nanoindentation equipment. And she was asked to enter something into a science fair. And she had a wonderful idea. The wonderful idea came from looking at a box of shampoo that she used to clean her hair. And on the box was written this: introducing formulas so gentle, yet so strengthening, this shampoo, strengthens the hair fiber after just one use, helping it resist breakage. You can see where this is going, right? So she's got this beautiful long hair. She cuts some pieces off and uses our nano tensile tester to test her hair before shampooing and after shampooing. And here are the results. There's the test. There's the test mounted in the nano tensile tester. There's the hair mounted in a nano tensile tester. And here's the result. Stress strain curves. Black is before shampooing. Red is after shampooing. So as they would say in the old Mythbusters program, busted. And with that, I will conclude. If you're interested in learning any more about this, many of those things are in an article that Warren and I wrote about 10 years ago, and there's the reference to that article. Thank you for your attention.